Okay, now I will start my presentation. This is the outline of this presentation. First, I'll show research background and objective. Recently, the use of FPGA in the field of embedded systems has been increasing, but when large task is implemented only by the dedicated circuit, the development cost of the dedicated circuit is quite high. Towards this problem, a solution is to use software processor together with dedicated circuit. If performance of the software processor is increased, larger part of the target task can be processed on software processor. If we reduce the amount of dedicated circuit to be developed, the development cost of the target system can be reduced. About the computation and memory performance, the improvement of computation performance is relatively easy, but the improvement of memory performance is difficult. Furthermore, memory performance is likely to be a bottleneck. For maximally utilizing the transfer performance of SDRAM, we consider that software processor equipped with vector processing function is useful. That is targeted for data-powered tasks such as image and audio processing. Our research objective is to design and implement a software processor, including scalable vector operation with efficient data transfer mechanisms using standard SDRAM. The software processor is based on RISC-V with our scalable vector extension. In this presentation, we examine the behavior of SDRAM and design efficient data transfer mechanism with RISC-V software processor. And then we evaluate its performance to examine the feasibility of our software processor. Next, I will discuss memory access on SDRAM. This figure shows the timing chart of SDRAM read access. To read data from SDRAM, we should send the read command with specifying the bank and row address, and then specify the column address after several cycles. After several cycles have passed, the target data is read out. In user access, bank, row, and column address should be specified, and subsequent access into the common bank can start only after the preceding access completes. So memory access cycle time becomes long and bus utilization is quite low. When the subsequent accesses continue to the common row and bank, we specify only the column address. Necessary time for continuous access reduced and the bus utilization is quite high. In this case, the bandwidth of SDRAM data bus is expected to fully utilized. When the subsequent accesses continue to the different banks, they can be overlapped. So memory access cycle time is reduced and the bus utilization is higher than that of user access. Next, I will design our efficient data transfer function for our software processor. Based on the observation about SDRAM access, we can realize highly efficient SDRAM access by combining continuous access to the common law in common bank and utilizing multiple banks. Large amount of continuous memory accesses fit into array data reference. Array data is fundamental of data processing, such as vector processing. Software processor with vector processing can realize efficient computation on array data using vector loading function. This figure shows the vector loading function. First, processor core issues vector load request to memory controller. Next, the memory controller expands one vector load request into multiple read requests to SDRAM. These read requests are issued consecutively. The target data is transferred in bursty mode of SDRAM with maximum burst length. The transferred data from SDRAM chip is written into a vector buffer. Vector buffer is implemented using on-chip program of FPGA. It works as vector register file from the viewpoint of processor core. This figure shows the internal structure of memory controller. CPU side and SDRAM side are driven by different clock cycles, so asynchronous FIFO buffer is between them. Next, I will introduce our research prototype platform for demonstration of efficient data transfer function. We developed a research prototype to confirm the effectiveness of our vector loading function. Processor core is our original RISC-V software processor. The core is a 5-stage instruction pipeline processor. Memory controller includes vector loading function. The system is implemented on Xilinx Arctic 7 FPGA. Vector buffer size 64 kilobyte. Main memory consists of DDR3 SDRAM with 16-bit word. Maximum data size of one bursty transfer is 16 bytes. So one vector load reads 128 bytes continuous data. Next, I will show the evaluation result. By using our prototype system, we evaluated execution performance and bandwidth utilization of SDRAM. Execution time is measured by using real hardware on FPGA, and bandwidth utilization is measured by using HDL simulation. We use the program of two-array addition for evaluation. We compared 5 configurations. On-chip means that only on-chip program is used. This configuration corresponds to the case of ideal performance. Off-chip means that only off-chip SDRAM is used. VB asterisk represents the configuration of using our vector loading function. Baby curve means that SDRAM accesses with different row single bank. Baby row means SDRAM accesses with common row single bank, and VB bank means SDRAM accesses with multi banks. This figure shows the number of execution cycles. The vertical axis shows the number of execution cycles, and the horizontal axis shows the number of elements per array. The execution cycles are measured while changing the number of array elements from 16 to 128. In this result, on-chip configuration achieves the highest performance as we expected. This is the case of ideal performance, and we aim at this by vector loading function. Off-chip is the lowest performance. This is the practical case of you only using off-chip SDRAM. The configurations of VB core, VB row, and VB bank is the cases of using our vector loading function. All achieves high performance as compared with off-chip. Furthermore, that they achieve near performance to on-chip configuration. That is near to ideal performance while accessing to off-chip SDRAM. This figure shows the bandwidth utilization for each configuration. The vertical axis shows the bandwidth utilization ratio of SDRAM, and the horizontal axis shows the number of elements per array. In this result, in this result, the configuration on chip is not shown. This is because off-chip SDRAM is not used in on-chip configuration. Off-chip configuration achieves quite low utilization. On the other hand, VB row achieves quite high utilization. VB row achieves quite high utilization. And VB bank also achieves high utilization as compared to off-chip configuration. In summary, as for execution performance, VB row and VB bank is the highest performance and almost the same performance to ideal case. VB curve is slightly lower than VB row and VB bank, but highly improved as compared to off-chip configuration. As for bandwidth utilization, off-chip configuration utilizes only 9% bandwidth of SDRAM, but VB row and VB bank achieves 96% and 49% utilization. We can efficiently utilize the constrained off-chip bus bandwidth. Access performance of array references to off-chip SDRAM can be significantly improved by vector loading function. Finally, I conclude my presentation. In this presentation, I show that we designed and implemented the vector loading function as a prototype. That is efficient data transfer fully utilizing SDRAM performance. And we evaluated performance using real hardware on FPGA board and HDL simulator. we confirmed that the success to utilize 96% of SDRAM performance. As our future work, we develop a RISC-V soft-core processor with scalable vector processing efficiently using SDRAM. Thank you.